This is a very general question that we actually talked more about in the first half of the chapter. We have our Bohr model of the atom, we've got our protons and neutrons in the nucleus, and we looked very simply with our Bohr model at the various energy levels. Okay? Go back to what you know about the quantum jumps and the bright line spectra. Energy level 1 has less energy, the electrons at energy level 1 have less energy than they do at level 3, 4, 5, whatever. So if we're asking you to compare, say, level 3 and level 5, well, level 5 has more energy than level 3. Closest to the nucleus, lowest energy. The electrons want to get close to the nucleus first. They want to be in those lowest energy orbitals first because of that pull from the nucleus. And I mention that because I want to give you some hints about some other things that are going to be on the test hints later on. Alrighty, number 6, the hint says the shape of each of the orbital types. And this question is going to be about one of the shapes. If we said a dumbbell-shaped or a peanut-shaped area around the nucleus, and maybe 3 of those, well, then we're talking about a p orbital. If we say a spherical-shaped region around the nucleus of an atom, well, then you know we're talking about an s orbital. If we say a many-lobed structure, like you saw in some of the websites that we have posted on the Moodle page, then that might be an F orbital, what we call the flower-shaped orbital. Test hint number 7 says similar to number 32, and that's, I'm sorry, is a typo. That goes back to when I had the test hints for the whole chapter all put together in one. But test hint number 7 is again, or question number 7 is again talking about orbitals, and this is my absolute favorite question on the test for this entire chapter. I love it so much, I'm going to put it on the final exam. Love it, love it, love it, love it. In essence, to answer this question, you need to understand what kinds of orbitals there can be at each energy level, because I'm going to ask you about one that cannot exist. So, at level 1, only s orbitals can exist. At level 2, you can have s's and p's. And if you look at the blocks in rows 1 and 2, you've got the s block and the p block. At level 3, you can have sp, and d. At level 4, you can have s, p, d, and f. At level 5, you can have s, p, d, f, g, or whatever comes next. Can you have a d orbital at energy level 2? No. If you look at energy level 2, the second row here on this periodic table, my first row is way up here with hydrogen and helium. There's not enough room. There's not enough room close to the nucleus to have anything beyond an s and 3p orbitals in this second energy level. Just like even closer to the nucleus at energy level 1, there's even less room. There's only room for an s orbital here, a sphere-shaped orbital. When you get to level 3, you're further away from the nucleus. There's more room for electrons. They're higher in energy. You can have s, p, d, f. You're not going to have a 1p orbital. You can't have a 3f orbital. There's not enough room for that. You can't have a 2d, which I think I said already. But every energy level has an s orbital. Every one, even like energy level 12. From energy level 2 and on, you can have an s and a p orbital. So, except for energy level 1, all the rest of them can have p orbitals, even if you had, say, energy level 9, if we needed that. That can have s and p, but you can't get those bigger, more involved, more differentiated and lobed orbitals at the closer energy levels that are closest to the nucleus. So I've given you a lot of hints on this, but I think you'll get it. Test hint number 8, how many electrons can go into each set of orbitals? Okay, each set. Now, any given orbital can only hold 2 electrons. Only hold 2 electrons. I gave you an example in class about dressing rooms, bunk beds. We talk about several different analogies there, but any given orbital can only hold 2 electrons. Hold on a second while I grab a couple more orbitals. Here is a p orbital, a peanut-shaped orbital, that can hold 2 electrons. even though there are 3 different peanut-shaped orbitals. My apologies, I should have gotten my props ready ahead of time. So we have 3 different peanut-shaped orbitals. They line up on the XYZ axis. All together, if they each hold 2 electrons, that's a total of 6 electrons. 2, 4, 6. The s orbitals can only hold 2 electrons. There's only room for 2. The d orbitals, I don't have all 5 of them handy here, but this is one of the 5 d orbitals. This can hold 2 electrons, and the other 4 can hold 2 electrons. 2, 4, 6, 8, 10. 10 electrons for the d orbitals. That's why we've got 10 elements across in the d block of the periodic table. The fact that s orbitals can only hold 2 electrons is why we only have 2 columns, 2 boxes across in the s block of the periodic table. Our 3p orbitals hold a total of 6 electrons. That's why we got 6 boxes across in the p block. And then the f orbitals, there are 7 of those. They can hold a total of 14 electrons. So in these kinds of questions, make sure you're reading very carefully to see if the question is asking about how many kinds of orbitals, how many orbitals of that kind, or how many electrons can fill that kind of orbital. Alrighty, moving on. Number 9, how to calculate the total number of orbitals at a given energy level. This is very simple. Our principal quantum number n tells us this. You need to remember a very easy equation, and that is n squared. N squared tells us the number of orbitals at an energy level. If n is 1, energy level 1, 1 squared is 1, 1 orbital, 1 kind of orbital. If n is level 2, 2 squared is 4. We have 4 orbitals, an s and 3 p's. 1 s and 3 p's, 4 orbitals altogether. If n is level 3, 3 squared is 9. We have an s orbital, 3 p's, and 5 d's. Add them up, you get 9. Pretty easy. Number 10, the equation for finding the number of electrons in an energy level. Now I'm talking about the number of electrons, and that is simple. We know the number of orbitals at an energy level is n squared, and we know that every orbital can hold 2 electrons. So our equation for the number of electrons is just 2n squared. So the number of electrons in an energy level. Both of these are in one energy level. Number 12. Number 11. How many electrons specifically are needed to fill each energy level? Okay, sorry, I'm getting a little mixed up here, because these questions are very similar. Data number 12, how to calculate n if you know the number of electrons. Well, solve for the variable. If you know that there are 18 electrons in a particular energy level, divide that by 2, so that's 9. Take the square root, that's 3. Okay? So we're just plugging it into 2n squared and we're solving for n. The energy level that has 18 electrons is level 3. If the answer is 8, then that must be energy level 2. If the answer is 32, it must be energy level 4 and beyond, although energy level 5, 6, and 7 could technically have more if we needed that many. And energy level 1 would have 2. 2 times 1 squared is simply 2.